Welcome to the next short video on our session on the philosophy of information processing in complex systems using the information dynamics approach. In this short video, we're going to start looking at making more specific what we mean by information dynamics and start to present the perspective of our framework. We're also going to look at the first measure that fits here being the entropy rate. So the key question asked by information dynamics is, how is the next state of a variable in a complex system computed? In particular, how is it computed in that transient of the system that we thought of earlier as moving from some initial state to a final state? How is it computed in that transition in time through the interactions of the variables in space throughout the system? So here we can think about complex systems which we can represent or model as a multivariate time series of states. So here in our system, we have a number of variables or nodes, each of which have a time series of activity. There are many complex systems that we can represent in this way. For example, this could represent different measurements of EEG potentials in the brain. Each node here could be a different measurement point or a beam-formed source within the brain, each of which has its own time series of activity. The nodes could be genes in a regulatory network, which interact in some network structure and have a time series of activities or activation levels or expression levels rather of those genes. They could be equities in a financial market that have some hidden pattern of interaction, and each of which have a price which changes in time, or a volume of trade or something like that. In any case, there are many complex systems that we can model in this way. And we want to ask, for one specific variable, or for each of them really, but each one in turn, and at each point in time in its activity time series, where's the information in that activity level come from, and how can we measure it? Where might we look to identify where the information comes from? And the simple answer for that is we might look to the past of that variable and to the activities in the past of the other nodes. So we asked then whether we can model the information processing in that variable X in terms of how much information was stored in the past of the variable and how much was transferred from the other variables. We can ask whether we can partition these operations on information and whether they overlap, and so on. So I've already given you some types of multivariate time series that we could analyze. We can even think about some of the kinds of multivariate time series we've looked at previously in this course. For example, we looked at the scissors, paper, rock game and trying to predict the next move of each player given their own past and given the past of the other players. We can also think about characterizing the updates in cellular automata in terms of operations on information. Here we have the same kind of structure where we have time series of activity for the different cells in the CA which are coupled. So information dynamics specifically studies the computation of the next state of our target variable in terms of how information storage was involved in that processing, being the information from the past of that variable, as well as information transfer from neighboring sources, and information modification in terms of non-trivial interaction between those components. So the measures examine the state updates of a target variable. We're always thinking about the dynamic process of that variable X and how it updates its activity through time. In particular, we're also thinking about the dynamics of these measures in space and time, not just talking about how much information is transferred from variable Y1 to X in some sense on average, but thinking about how much is being transferred right now in this particular state update versus the next state update, and so on. We'll use a common set of notation in our sessions on information dynamics. We're going to be considering collections of time series processes here, symbolized by our capital letters X, Y, and Z. Each of these processes consist of random variables, one random variable at each time index. Each of those processes have process realizations. We use lowercase letters to represent our realizations here in the same way that we did for variables versus samples when we started considering information theory in the first place. And we have countable time series, time indices n for each of these processes. We'll denote consecutive block vectors of our random variables in this sort of notation here, using bold to indicate a vector that ends at time n and includes k previous time steps. So it's a block of size k up to and including time index n. We'll see later on in our sessions why we're going to call this a state representation of the variable. These state representations have realizations, which we'll use lowercase letters to indicate, but otherwise with the same notation. So formally what we're asking in information dynamics is, where does the information in a random variable x at time step n plus 1 comes from in terms of the other variables in the system at time indices previous to that? And of course we're considering the past of x as well, not just the other variables. So we'll have a brief look at one of the first measures that we can consider in this context, and that's the entropy rate, one of the classic measures of information theory, which historically should be the first thing that we start to look at here. The entropy rate measures the limiting rate at which these block entropies scale with block length. So here we're looking at the block entropies of variable x and how they scale with block length n in the limit that n becomes infinite. So this is what it looks like mathematically. Sometimes it's easier to focus on this graphically. Here what we're doing is we're looking at these block entropies for block sizes n of x and how they scale with variable n, and that's denoted by our green squares here. So what we see is that initially for very low n, the block entropies scale up quite quickly, but then the rate of increase tails off, and that's because we often, not necessarily always, but often end up getting a lot of redundant information in the previous n-1 variables that overlap with our nth variable. So what we're looking at here for our entropy rate is, what is the limiting slope of the asymptote here as n goes to infinity. That's what the entropy rate is measuring. Okay, it's measuring the limiting slope as we're adding how much it's measuring the limiting slope of the block entropy versus the block length. There's another way we can look at that, which is to measure the uncertainty of the next random variable given the past of the process, and we can write that as a conditional entropy here. Now, we can, again, this is the mathematical way to write it down. It may be easier to view this graphically. And here, what we can imagine is we're now adding in one more variable, our nth variable, and how much information is that nth variable giving us compared to what we already had in our n-1 previous variables. That extra information is the increment in one step here. Okay? So we've got two different ways of coming at our entropy rate, either as the slope of the line or the increment per variable in the limit. For stationary processes, they are exactly equal, and generally that's what we're going to consider. Okay, those two different perspectives are the same for stationary processes. In terms of thinking about information processing in our variable x, the implication here from looking at the entropy rate is that we're using the past of the process as a first information source on what's going to happen in the next sample, and we're asking how much uncertainty remains in predicting the value of that variable after we have already looked at the past. We can think about what the coding interpretation of that is by looking back to when we thought about coding letters in English text. If you recall, we observed that if you think about how much information you already have from letters you've already seen, that can often be very predictive about the letter coming next. Okay, for example, if we see a Q in written English, we can guess almost with 100% certainty that the next letter will be a U. So here the coding interpretation is that the entropy rate is the amount of code we would need to send to encode the value of our next sample if the receiver already knows the samples that have come before and can use them to help decode the next sample that we're about to send. Okay, and this is always less than or equal to the per symbol entropy of variable x. Okay, because using the pass on average can only inform us about what's coming next. So, in this short session, what we've done is looked at the philosophy behind the information dynamics approach for analyzing information processing in complex systems and started to set up our framework for information dynamics. We've looked specifically at the entropy rate as a first pass in understanding the dynamic update of time series processes. In our next sessions in this set on information dynamics, we're going to be considering other operations on information, in particular information storage, coming up next, and information transfer as well.